a partir ya desde hace un poquito más de un mes al Departamento de Química, de Radiaciones y Radioquímica. Pero también quisiera aprovechar para comentar que estamos muy contentos, que hemos como concluido de manera, yo diría, muy exitosa esta primera fase de renovación del instituto. Tuvimos la posibilidad de renovar 5 plazas, una de química, una de estudio de la materia, una de plasmas y 2 de gravitación. Pudimos establecer unos nuevos lineamientos con perspectiva de género que se aplicaron. Tuvimos más de 250 solicitantes de más de 15 países y tras pues un proceso riguroso llegamos a estas 5 personas que ustedes ven en la pantalla, que se incorporan algunos, bueno, ya está Anastasiya desde hace más de un mes aquí, y las más personas se incorporan en los próximos meses hasta la última será en agosto del año que entra. Entonces, pues, sin más, le paso el micrófono a Yuri para que presente a Anastasiya.
Bueno, pues, hola a todos. Como se suele estilar en un coloquio, voy a leer la semblanza de Anastasiya. La doctora Anastasiya Sedova obtuvo la licenciatura en Ingeniería de Materiales en el Israeli College of Engineering en Jerusalén, trabajando desde entonces con el profesor Tene, cuya adscripción es en el Instituto Weizmann. Realizó la maestría en Ingeniería de Polímeros en el Shenkar College of Engineering and Design, también en Israel. Obtuvo el doctorado en Nanociencia y Nanotecnología por el Sinvestav en 2021 y realizó estancias postdoctorales en el Instituto Weizmann y en la Universidad Ariel, ambas en Israel. Su trayectoria profesional abarca la síntesis y caracterización de nanomateriales, el desarrollo de compuestos poliméricos y el estudio de propiedades eléctricas, ópticas y magnéticas, así como un amplio dominio de técnicas avanzadas de microscopía y espectroscopía. Ha publicado 15 artículos en revistas de alto impacto, de los cuales 9 son como primera autora. Sus trabajos suman 224 citas según Google Scholar. En septiembre de este año se incorporó al ICN como investigadora asociada C en el Departamento de Química de Radiaciones y Radioquímica, en lo que esperamos sea otro escalón fructífero en su carrera científica. Hoy nos presentará el coloquio Nanomaterials from Lubrication to Optical Emission and Future Plans, donde compartirá su trayectoria y los proyectos que tiene previstos en esta nueva etapa en el ICN. Sin más, le damos la palabra a Anastasiya.
Muchas gracias por la presentación. Gracias que están aquí. Me da mucho gusto estar aquí con ustedes. Me dijeron que la meta de esta plática es presentar a mí, entonces pensé que la mejor manera es presentar lo que hice y que voy a hacer en ICN. Mi plática va a estar en inglés, pero espero que para la próxima ya en español. So I'm going to present my past scientific work and my future plans in ICN. My bachelor degree is in materials engineering, and I arrived to the lab of Professor Reshef Tenet to do my engineering projects. Shortly after I started with Professor Reshef, he and his former student, Oad Goldberg, they offered me to work as a research assistant in the lab. And after I started my degree in polymers engineering, and I continued working with Professor Reshef Tenet, and my thesis work was basically a collaboration with him. Reshef Tenet is one of the pioneers of the nanofield, and following the discovery of the carbon nanotubes, and Fuller predicted that layered materials, inorganic materials, such as transition metal dechalcogenides, those layered materials are composed of transition metal sandwiched between 2 dechalcogen atoms. Inside each layer, the atoms are bonded by covalent bonds, and between the layers are held by weak van der Waals forces, and he predicted and synthesized Fullerene-like nanoparticles and nanotubes. But I wanted to present you Reshef not only because he's a great scientist, a great person, but also because he shares the vision of Dr. Alfred Uren, and it's of collaborations and patents. This pretty much summarizes where the materials that Reshef synthesized about 35 years ago can be applied in. There are actual oils, I checked, it's sold on Amazon, that contain inorganic nanoparticles of molybdenum disulfide. They're anti-friction coatings. Nanotubes of tungsten disulfide are widely studied for optoelectronic devices. All of those materials can reinforce, basically serve as composite materials. For example, reinforced Kevlar for ballistic response. Also, Reshef was part of establishing a facility where they could synthesize large amounts of those particles. So I'm not saying that everyone needs to open a factory, but certainly materials that we synthesize in the lab can be commercially available. So how those materials work in lubrication, we believe there are three main mechanisms: rolling, sliding. Due to their nano nature, they can basically go in between with ease in between two surfaces and serve as a separation. Due to their layered nature, they can exfoliate, and the layers will go with ease in between two surfaces. When I arrived to the lab, we wanted to study lubrication in case of medical devices, basically lubrication between soft tissue and the laparoscope or a urinary catheter. So how we did it? So first of all, we needed to imitate tissue, basically. So we chose to work with these polymers that are called PDMS, polydimethylsiloxane. It's a soft polymer used for molding in cosmetics. We needed to design those molds with a retractable pin in order to adapt it to the radius of the device that we were basically testing. Then second step is very easy. We just mixed a commercial gel that actually used for friction in surgery, basically to reduce the friction and facilitate with pain. And then how we were testing, basically. So we designed this device that could fit into an engineering machine. It's called Instron. This machine is used to test materials as resistant of materials to tension. Basically, there are two parts. One goes down, one goes up, and there is a load that measuring the force. And we designed this device to fit exactly into this machine. And what we basically were measuring is the force that needed to extract the device that we are testing from this ring, soft rings that we designed. And we saw that there is a reduction of about 47% in the force that needed to extract the device. Then I started measuring working on optical properties of those materials. Those are semiconducting materials, and with simple spectroscopic measurements, we can identify the excitonic positions. Excitons are pairs of electrons and holes, and Mie scattering. I will go to Mie scattering later. And the idea is that this material basically supports excitons at room temperature. Then we started working with these interesting materials, aerogels. I think they're interesting and challenging in the preparation step. So it's starting from a gel. It basically looks like gelatina. In the first step, when it's forming as a gel, it's already a porous material. Nonetheless, the pores are filled with the liquid. So the idea is to arrive to the dry product without the pores collapsing into itself. So what we needed to do, we were working in ethanol. The gelation was in ethanol. Then we will replacing the ethanol with liquid CO2. Then we needed to arrive to a supercritical conditions where basically we cannot distinguish between the properties of the liquid and the gas. And at this point, we could basically illuminate it, illuminate the supercritical fluid and obtain a dry products. So Those materials are used for insulation. They have lightweight, about 97% pores, that they can, for example, be used in aerospace without compromising the weight. Nonetheless, they struggle from poor mechanical properties. So we said we will add nanotubes and see if we can improve the mechanical properties without compromising the weight, as we're adding nanomaterials, and without compromising the pores, basically. So the aerogel without the nanotubes is white and transparent, and with nanotubes it's already become gray. So we designed samples, we prepared samples exactly to fit the testing machine. We did 3-point bending. Basically, we have 2 positions where we place the sample. In between there is nothing, and there is upper movable part that will press into the sample until it will break. Compression test, basically will compress the sample until cannot anymore. Could achieve improvement, quite a high percentage of improvement in strength, tangent modulus, and toughness. Also, we analyzed the optical properties in this matrix of silica aerogel. So when we do spectroscopic measurements, usually we do it in solution where particle can constantly rotate. And here we could fix basically the particles in a constant position. And what we saw that as we increase the concentration of the nanotubes, the excitonic positions washing out. We basically cannot anymore distinguish it due to the multiple scattering effects. Roy Levy showed on a single nanoparticles that if he applies stress in the form of tension or a torsion, the electrical response, electrical conductivity will be increased. He showed it on a single nanoparticles. It's a great achievement. It's very hard to do. And my thesis project was on how we take this single particle effect into multiple particles. So we started to do similar work as done with carbon nanotubes, basically dispersing the nanotubes in a polymeric medium in order to try to achieve a percolation, basically a continuous network of the nanotubes where electron can hop from one nanotube to another. But unfortunately, we didn't succeed that way. Basically, the nanotubes were encapsulating in the polymer, and basically the conductivity was not happening. So we changed our approach, and we said we will use the polymer as a binding agent and not a dispersing media. We needed to design this device for the sample preparation where we could prepare samples under different loads. And eventually we obtained those samples. We dried them, basically annealed them, and that way you harden the polymer and you obtain a hard sample. We could achieve samples of, which I think it's a great achievement, as we know that the electrical resistance will increase with the size of the sample. When we applied a relatively low pressure, we could see that the nanotubes basically touching each other. So it's what we were expecting to achieve, that the nanotubes will touch each other and the electron will be able to hop from nanotube to the other. But when we increase the load, basically it's the same thing happening as with dispersion. The polymer went in between the nanotubes, and we could not achieve the results that we were expecting. So we were working with samples that were prepared in with a low load. And how did we measure it? We basically did a 3-point bending test where we press into the samples until it breaks, and we measured the conductivity in the same time. And we basically could observe the same thing as Roy Levy observed on a single nanotubes, that the electrical conductivity is increased with the stress. There was a point of time that I thought my master's degree work is not going to succeed, so I started developing synthesis of the magnetic nanoparticles on top of the nanotubes. Inherently, the nanotubes are weak diamagnetic material. The electron spin will align in the opposite direction to the magnetic field. If it was a strong diamagnetic, we could use these properties. Nonetheless, in our working range is basically non-magnetic material. Synthesis is based on the defects that the nanotubes have. So in the first step, I deposited iron hydroxide nanoparticles on those defects, and we could achieve super paramagnetic response. And in the next step, I basically annealed the material, and we could achieve ferrous tungstenate nanoparticles that presented competitive response of ferromagnetic and antiferromagnetic materials. So the idea for me even to start depositing magnetic nanoparticles on the surface nanotubes is I was trying to align those nanotubes inside of the polymer and try to achieve percolation that way, or by alignment you can achieve different mechanical properties. But we didn't succeed to do it with polymer as it was too viscose, so we did a solution, basically drop casting it onto a glass substrate and applying a magnetic field. So with iron hydroxide nanoparticles, we just saw that there is better dispersion, but there is no specific orientation. So we did it with nanoparticles that we annealed with iron ferrum tungstenate, and we could see that there is something that reminiscent of the magnetic field. For example, in this synthesis, I could not cover completely the nanotubes and obtain like stronger magnetic response. Nonetheless, for example, if I had the gamma irradiator, I could generate more defects on the surface and then use these properties to grow more nanoparticles on the surface, and maybe that way I could achieve what I was looking for, alignment inside the polymer, inside the viscose media. So it's what I was doing between 2013 and 2016. And then I arrived to Mexico. Why? I got married with a Mexican guy, had a position here in Simba staff. And I started working with Dr. Zero Falcone Guajardo. He's an expert in photoluminescence materials. We were synthesizing nanomaterials of gadolinium niobate. By careful control of the experimental conditions, we could synthesize different morphologies. We can synthesize different sizes. We could dope this material and obtain an optical emission in different regions. So why we even need all these morphologies, all the sizes of the materials? So if we talk about optical emission, the size matters. The smallest the particles and more precisely the crystalline size, the optical emission will be more efficient. For example, here flowers, they're like medium particles here, but they have the smallest crystalline size, and they showed the most efficient basically optical emission. Where else the size can matter? In mis-scattering. So briefly about mis-scattering. If we talk about particles smaller than 15 nanometers, the Rayleigh scattering is the theory to describe it. Nonetheless, for the larger particles, the Mie theory is the way to go. Mie theory is Gustav-Mie solution to Maxwell equations. By spectroscopy measurements, we can identify the Mie scattering peak, and it will depend on the size. The width of the peak and the position of the peak will depend on the size of the nanoparticles. So we wanted to work in the visible and near in IR region. We synthesized particles between 200 nanometers to 1,000 nanometers, so we were in the Mie-scattering region. In Mie-scattering theory, there are Mie-scattering coefficients that are dependent on the size parameter, that dependent on the radius of the particle, and refractive index of the medium. The theory was originally developed for spherical particles, but we applied it to a different morphology. Also, it depended on the relative refractive index, that is the ratio between refractive index of the particles and of the medium. And if the refractive index of the particle and the medium are very similar, we basically won't be able to observe the phenomena, as the AN and BN coefficients will disappear. So we need to work in conditions where our media in our particles have this refractive index as distinct as possible. And with those coefficients, we can calculate scattering cross-section, extinction cross-section, and the absorption one. All those parameters can be measured experimentally. Nonetheless, if we can measure only 2 of them, we can deduce the 3rd one. So we synthesize particles with different sizes from system 1 is the biggest particles and system 4 are the smallest one. We measured the extinction spectra and we saw the mis-scattering peak is basically blue shifted to the lower wavelengths. So how we know that it's mis-scattering peak and not other phenomena? We measure absolute absorbance, and for absolute absorbance, the scattering peak disappears. We did numerical calculation to see what basically contribute to this mis-scattering phenomena. We did it on the single particles, and we could see that there is contribution of the dipole, octopole, and quadrupole. We calculated the electric and magnetic contribution, and we saw that the contributions are basically different for a single particle. We did the same thing for the multiple particle case. Also here we could separate the contribution of the dipole, quadrupole, and octopole. Nonetheless, when we calculated the separate contributions, we saw they're quite similar in this case. So basically what we have here is the common phenomena, is average phenomena of all the particles of all the sizes. So where we can apply mis-scattering, one of the applications is surface-enhanced Raman spectroscopy. More people are familiar with it for the metal nanoparticles such as gold and silver. 2 close nanoparticles can create a hot spot. And if you couple it with the low concentration analyte, basically the Raman signal can be enhanced by a factor of 15. So when we have metal nanoparticles, the direction of the electric field is important, and the hotspot will be created, basically formed in a specific direction of the electric field. But if we talk about nanoparticles that have the electric particles that have mis-scattering, due to the separate electric and the magnetic contributions, basically we can create hotspots in 2 different directions. Also, by using those nanoparticles, we can prevent photochemical, thermal, or photothermal energy dissipation. Another application for the mis-scattering is, and that it's of interest to me, we can couple transition metal decalgonides, the materials that I was talking about in the beginning, with the particles that have mis-scattering. So the transition metal decalgonides support exciton at room temperature, and the particle can supply a resonance cavity, and that way we can basically confine exciton polariton, and it can be used for exciton polariton lasers, for example. So when we can confine, when we have our mi-resonance particle, by simply measuring the photoluminescence, we can identify the excitonic position and the low polaritonic state. And when we don't have the particle, we basically obtain standard photoluminescence emission. So it's what I was doing between 2017 and 2021. And then I started my postdoc with Dr. Lena Edgarov at Ariel University. The project was also a collaboration with Weizmann Institute of Science, and we were working with this electron paramagnetic resonance technique. The technique is based on Zeeman effect. When electron is placed inside a magnetic field, it has a magnetic moment that will align parallel and anti-parallel to the magnetic field. Each will have a specific energy. So in these measurements, we basically keeping all the parameters constant, the frequency, the Bohr magneton, the G factor, and varying only the magnetic field until we arrive to the resonance conditions. In this resonance condition, electron basically can absorb energy, And what we will see as a spectra is the first derivative of the absorption. We were working with the spin trap that is called BMPO that can basically trap radicals such as hydroxide and superoxides, and the spectra of it is known. So any change in this spectra is visible. So the preparation of the samples for the measurements are frankly simple. We were studying degradation of perovskites. So first we dispersed our material in solvent that we add BMPO. We place it into a quartz capillary, and in this stage we could basically illuminate the material with light in order to generate electrons, in order that our semiconducting material will be contributing basically electron to the system. And we measured the APR spectra. So we were studying degradation, in situ degradation of halide perovskites such as cesium lead brom 3 and cesium 4 lead brom 6. They're very efficient materials optically, nonetheless they're very sensitive to the environment, to the polar solvents, if they're exposed too long to the light. And by measuring EPR spectra every 3 minutes, we could closely see the changes that are happening. By computational means, we can fit this spectra and basically identify what radicals are contributing to the decomposition. Also, this technique is very efficient basically in studying electron transfer in case of semiconducting materials. Then I went to do my postdoc with Professor Boris Rybczynski. When I just arrived to the group, they were starting with this innovating technique that is called 4D STEM. When I present this technique in brief, I believe it doesn't do it justice because I cannot completely transfer everything I want to say, but due to the time limit, I still present it in brief, and if someone wants to hear it in full, I can do a full presentation. So the technique is developed in transmission electron microscope. We have a focused electron beam that scans the samples, and we can collect a diffraction pattern at each scan position. We have a high-speed detector, and we can collect as many as 16,384 to 262,144 diffraction patterns. And those patterns we can analyze by computational means, and this is the most time-consuming process. So what can we study from this information? We were working with polymers. We wanted to study crystallization of polymers by this technique. We started with PLA. This is a TM image, dark field STEM image. You can see some curvatures. Those are crystals of polymers. They are called lamella. By computational means, we can obtain those orientation maps. Orientation maps basically vectorization of the diffraction planes. We can know the orientation of the crystals. The color wheel will indicate the azimuthal angle. We can obtain fluctuation maps. Fluctuation maps is variance of intensity normalized by mean intensity. And in case of polymers, it's important because polymers are semi-crystalline materials. They have amorphous region and they have crystalline region. And here we can see that it's very sensitive to the crystallization. And we can see that the dark parts are the amorphous parts and the shiny parts are basically the crystalline regions. We can isolate lamella. Those are crystals of polymers. We can go to one of them and extract the diffraction pattern there. We can go to other lamellas and extract the diffraction patterns there and analyze it. We can plot all the diffraction spots that we collect as a reciprocal space histogram and scatter plots. PLA has an orthorhombic crystalline structure with two main diffraction planes, 200 and 203. The 200 cut a single chain in the unit cell. So what we can do with these properties and the technique, we basically can isolate a lamella, go along a lamella, extract a diffraction pattern at each point of the lamella, and by simple analysis, basically by connecting two equivalent diffraction spots, we can identify the orientation of the lamellar chains. Basically, when the polymer crystal is formed, the chains are folding, and we can see how those folds basically oriented compared to the lamellar normal. Until recently, it's believed it's just perpendicular, but one study before us on other system showed that it's not true, and we could show it here as well. We can extend this technique to 4D STEM tomography and obtain basically 3D images of those crystals, and we can see how they're in space. So this was what I was doing from 2021 to 2024, and finally what I'm going to do here, why I was hired. So I'm interested in studying materials for radiation detectors. There are two types of materials that can be used for this application. Scintillators that basically translate the ionization radiation into light. Those are wide bandgap materials. Another type of materials are semiconductors that translate ionization radiation to current. Those are narrow bandgap materials, and those are the materials that are of interest to me. So there are basic requirements from those materials. They're supposed to be high-density materials, high intrinsic carrier mobility. They're supposed to present low number of defects and high resilience. Nonetheless, it's very hard to achieve a single material that presents all those properties. So those materials can be in form of a single crystals, polycrystalline thick films, basically can be composites of polymers within nanomaterials, polycrystalline thin films, and thin films of conducting polymers, for example. I'm interested in studying with the two first configurations. I'm also interested in studying photonic waveguides, and one of them is where I have a semiconducting material that can be optically pumped, embedded in polymer. Polymer we can basically mold into any shape. And the polymer have a dual function. It protects the semiconducting material from the ambient environment, and it can basically guide the light. Another type of waveguides that I'm interested in are organic crystals, and here we need to control the size and the shape of the crystals. So the semiconducting materials that I'm interested in for radiation detectors and for the waveguides are double perovskite oxides. More people are familiar with the single perovskites, where the general formula is two distinct metals and 3 oxygen atoms, where the double perovskites are basically the doubling of the formula. And they have diverse chemical composition, tunable bandgap, high stability, unique magnetic properties, and half metallic behavior. Besides, we can dope them, for example, with rare earths and take advantage of the unique electronic properties of the rare earths. We can use rare earths as a matrix. We can take advantage of the magnetic properties, for example, or take advantage of the different radius, and that way manipulate the bandgap, basically changing the composition. We can play with the A atoms and replacing B atoms. So basically the variety of composition of this material is immense, and we can design the material with the properties that we need for our applications. So we can change electronic, optical, and magnetic properties, and very often simultaneously. So for the polymeric part, I'm interested in working with biodegradable polymers such as PLA. PLA already showed some wave guiding behavior. Taking advantage of the gamma radiators that we have here, I also want to study how those materials basically degrade after exposing it to the gamma radiation. So polylactic acid is one of the most promising polymers. It's already 30% of the polymer that is used daily is PLA. Nonetheless, even though it's considered to be biodegradable if you just throw it on the street, instead of degrading within 80 days, it will degrade in 70 years. So the So it's still, considering how much garbage we produce daily, it's a problem. Still we create a problem. And in these studies, we need to consider the molecular weight, crystallinity, and the additives that the companies add to produce the products. And basically, the materials that are semi-crystalline will degrade very differently compared to the amorphous one. Polymers that have short molecular, basically short chains will degrade faster compared to polymers that has long chains. So all those parameters we need to consider in these studies. And another type of materials that I'm interested in are organic crystals. So it also was part of my postdoctoral experience. We wanted to use those crystals to reinforce polymers and they use them to initiate nucleation. Nevertheless, here I want to repurpose them and use them as waveguides. So this is how we obtain those crystals from the company, and by simple recrystallization process, we can obtain those rod-shaped like particles that can be used as waveguides. Another example is uric acid. It's formed in our kidneys, and it's how we obtain it from the company. And by simple recrystallization process, we can obtain those flakes. And by using a substrate such as Kevlar, we can obtain those rectangular shaped particles. So I wanted to highlight here that by simple manipulation, we can manipulate the morphology to design it for our needs. And in my case, waveguides. So the biocompatible crystals can be of bio-origin, can be synthetic, such as vitamins B, and those are materials that I'm interested in starting with. They also can be shaped into these rod-shaped like particles, that they can be doped with organic dyes. Those organic dyes can be excited and emitted in the biological windows. For example, in this study, they injected directly the dye and could do imaging, and they showed that there is a low cytotoxicity. Nonetheless, if we use this dye only as a dopant, so basically we reduce significantly the amount of the dye and we put it in vitamins B that our body needs to develop for the brain, for the cells, we can reduce significantly the cytotoxicity. Also, we will expect from this waveguide basically to amplify the light, and we expect to get better imaging and better cancer treatments. So basically the idea here, there are many studies on inorganic materials that are very efficient, but what happened after the treatment, where this inorganic material goes. In this case, it's fully organic material. It's a material that body needs, and it will completely dispose after imaging or the treatment. And I want to finish my talk with my best project so far. He has 1 year and 3 months. He has a lot of potential, but it's definitely a work in progress, and he's amazing. And I want to thank all the people that have been involved in the results that I showed, and thank you for listening and coming. Thank you.
Thank you. Les damos las gracias a los que estaban en YouTube. ¿Ya se las diste? Qué rápido. Bueno, entonces podemos tener una sesión de preguntas sin necesidad de estar corriendo.